Hello, hello, hello. Good afternoon, everybody. Welcome back. We are going to head now to our next talk. And before, let me again introduce myself. I'm JP. I am moderator. I'm a web engineer myself, working as an artist right now. But besides that, a brief thank you to all of our partners that is allowing us this event possible. And a small question for everybody. Have you all downloaded the We Are Developer app? Answer? Yes, thank you. That's the spirit that we want. And I am asking you that because through the app, besides checking all of the amazing events happening, workshops and everything, you can ask questions. So if you find something very interesting in the talk and you want to ask a question, you can ask it in the app. And then at the end, we can have some times and then read some Q&A. But beside that, we are diving a lot into AI and machine learning. We started from the morning talking about how is machine learning affecting our everyday life, what is the dangers about it, how AI is getting into the automotive and how it is helping the auto industry and changing the auto industry. But I think the next talk is amazing because we are going to have a data scientist that is going to share with us some trends, challenges, and best practices for AI at the edge. And now I would like to give the stage to Ekaterina Sirazitdinova. Round of applause, everybody.
Thank you for this lovely introduction, and I'm so happy to be back here at VIA Developers. I was presenting here already last year, and it was amazing. The topic of my today's talk is trends, challenges, and best practices for AI at the edge. So what do we understand as AI at the edge? Raise your hands who knows what AI at the edge means. OK, half of you probably know. So by AI at the edge, we understand AI computations happening near to where the data is being collected, at the edge of the network. So imagine a fleet of embedded devices and robots operating in the field, and they don't necessarily have a network connection to a data center or to the cloud. So you need to run these computations in these constrained environments. And this is usually a challenging process because these devices are small in sizes and have a smaller compute. So how do we actually optimize our AI models and AI applications to run on these small devices? And we at NVIDIA, we have collected some best practices and techniques. And in my today's talk, I'm going to share with you these best practices and techniques. And well, let me start telling you that actually edge AI transforms almost every industry. You may even not be aware of that, but it's everywhere in our life. So in manufacturing, we rely on distributed edge systems for applications like smart factory and automation, quality control, defect detection on assembly lines. In retail, you may know about applications like automated checkout or frictionless shopping, where you walk into a store and you grab some goods and you're being charged without even going to a cashier. Like Amazon Go is implementing such solutions. In smart cities and smart spaces, we have distributed edge AI and IoT devices everywhere. Think of applications like smart parking, smart traffic lights. So this is all being powered by AI at the edge. In healthcare, we are working with surgical robots. These are handheld devices which apply AI in order to assist doctors performing surgeries. Then we have logistics, where we have smart picking and placer robots. And in agriculture, we can put our embedded devices on a tractor, and then we can recognize different crops. Is it a crop or a wheat? And then we can treat it accordingly. At home, you can think of robots which serve you as entertainment and care systems. And at last but not least, in metals and mining, we can have unmanned ground vehicles which autonomously perform hard tasks, replacing humans. So the applications, there are many applications in the area, and there is a huge potential for businesses in this domain. And there is a major macro trend which we observe in the past couple of years. So we started with the fixed devices, like smart cameras mounted on the wall, which then started gaining some mobility and evolved into complex systems. And as a consequence, AI compute power demand also grows. So in the past couple of years, we observed the trend of these devices being more complex and demanding more power. Think of the applications like I've mentioned, handheld medical instruments, surgical robots, delivery robots, warehouse and logistics systems where we have a fleet of interconnected devices monitoring different things in the factory, and autonomously moving robots and vehicles. And it's important to say that edge devices, there is a big difference between edge devices and a physical data center. First big difference is lower compute. So these embedded devices, they are usually small in size. Like, for example, our Nvidia Jetson devices, they can be of like credit card size. As a consequence, they have a smaller chip, and it means that you can put less computations than, for example, on a powerful H100 or A100 GPU in the data center. So the compute is limited. The storage of these devices is also limited. So sometimes these devices are not connected to the network, which means that they need to collect all the data and store it on their integrated hard drives. And as a developer, you need to think of things like, do I store all the data collected, or maybe just some selective data? Like, if I have a video feed, do I store all the frames, or maybe some selected frames? And they also have restricted power consumption. So think of devices like autonomous drones. They are not connected to power outlets 24/7. So when developing applications for AI at the edge, you need to be mindful of their power consumption. And when starting developing AI applications for the edge, you will definitely face many challenges. And the major challenges are the following. So the first one is accuracy. So you need your AI networks to be accurate enough to provide meaningful insights. So first of all, you need to find a good architecture which will reflect the goal of your application, and it has to have a small number of false positives, and the accuracy needs to be high. You also need to collect a lot of data in order to make it happen, because you know that AI is powered by data. Once you have solved the accuracy challenge, you need to think of increasing the throughput of your application. And well, for some applications like ChatGPT, for example, you can allow waiting for a couple of seconds to get the response. AI at the edge often requires immediate and real-time response. Think of applications like autonomous driving car and a situation when a child jumps next to your car. You need to brake immediately. Or a surgery device, you need to react immediately there. So real-time performance is crucial for edge devices. And as developers of edge AI applications, we really need to focus on making these applications work in real time and decreasing the latency. And the final challenge is deployment at scale. So think of the situation. You've developed one single good application with good accuracy and good throughput. Now you need to solve the problem of how do I deploy this application across multiple geographies all around the world, and how do I maintain these applications? How do I update my models? How do I, take the application down, and so on? So you need to take care about these things. And at Nvidia, we have, as I mentioned, a set of best practices and solutions for you, and let me share now them with you. And the first solution is to increase accuracy. And it's a big trend also in AI in general, not only in AI at the edge. And the solution is using of synthetic data to train AI models. So instead of relying purely on real data, you can assist your network and you can augment your data sets with some synthetic data. Synthetic data offers you many benefits in the sense like you can add corner cases. Imagine a situation which rarely happens in real time and is really hard to collect real data for the situation. You can easily model it in your synthetic data systems, like relying on CGI, for example. Synthetic data also solves the problem of expensive labeling. So by using synthetic data and automatic algorithms to label your data objects of interest, you eliminate the need of hiring many human labelers. And synthetic data offers you also an environmental diversity, where you can easily swap textures, objects, and you are the creator of your data. And now talking to the throughput and the techniques which help you to increase your throughput. So one of my favorite techniques is the so-called quantization. And quantization basically means reducing bits per weight. So typically, your networks are being trained in powerful data centers in the floating point 32. And a clever idea was to reduce this precision to floating point 16. And this is easy to do. You basically just round up your network weights to floating point 16, and then it works. But then another clever idea was to reduce the bits even further to the integer 8. And you can imagine that we cannot just simply round it up, because it will lose a lot of accuracy. So the clever way to address it was to provide a mapping from the interval in floating point 32, minimum to maximum, to the integer interval, which is between minus 127 to plus 127. And there are basically two ways in doing that. The first way is the so-called post-training quantization, where you train your model just in a normal way in floating point 32, and then you use a separate data set as a calibration data set to find this minimum and maximum values in your network. And then you derive and then you interpolate it to the mapping to integer 8. Another way to do it is by running the so-called quantization-aware training, and some of the frameworks allow that. Essentially, in quantization-aware training, what you do, you have an extra loss function which you use then to estimate this, to learn these mappings from the floating point 32 to integer 8. As a consequence, you get a more accurate mapping, and your model is easily convertible in in integer 8. The next powerful technique is the so-called network pruning. In network pruning, you basically remove some neurons from the network, and as a consequence, you also remove some connections between them, which makes the network smaller in size and faster in execution. How do you remove these networks? Basically, you run your network, and then you observe which neurons in the network do not participate in the final outcome of the model. And then you compare this value to some certain threshold, and then you can eliminate them from the network. It's a lossy process, unfortunately, and you will lose some accuracy. However, it is easy to restore by running training for a couple of extra iterations. So it's another powerful technique which can help to shrink your network in size and to make it faster in execution. Another technique is the so-called network graph optimizations. And in this approach, you parse your network graph and try to fuse some of its layers horizontally, but also vertically. And the reason why it works is basically all these kernels, they rely on CUDA calls to your GPU. And these kernels are super fast in execution on the GPU. However, the transitions between these kernels may slow the process down. So in order to make it faster, you try to combine as much as possible without altering the mathematical computations in the background. By doing that, you can achieve the really highest throughput as well. The next technique is the so-called kernel auto-tuning. And those of you who actively work on developing neural networks and deploying them, you know that we have the multitude of configurations. We can have different batches. We can have different tensor layouts. And you also deploy your networks on different devices. We have devices like embedded Jetsons or x86 architectures. They are all different, and our networks perform differently on these devices. You may also know that there are multiple ways to implement a single operation, like convolution, for example. And also different implementations can work differently on different devices. So the idea here is just to brute force your current setup on the target device and see which combination of the algorithms and configurations gives you the best performance on the given device. So this is called kernel auto-tuning. Another technique is the so-called dynamic tensor memory upon inference. And this technique has been inspired by register allocation in compiling. So here, we combine tensors in our network into some regions. And these regions have disjoint execution time. And we then assign these regions to blocks. And, well, basically also regions, these regions assigned to blocks also have disjoint lifetimes. It also helps you to speed up your training and decrease the memory footprint. And another technique is the so-called multi-stream concurrent execution. In CUDA, we have the so-called paradigm called CUDA Streams. And basically, it means that we can run multiple processes at the same time on the same physical device in parallel without interfering with each other. And when executing our network, we can actually parallelize some processes inside of the network. So, for example, we can parallelize host-to-device memory copy. This is a special terminology which we use for copying between the CPU and GPU. Retrieving device to host from the GPU to the CPU, and the kernel execution. And by kernel, we understand the actual computations running in your network. So by doing that, we can also shrink our network in the execution time. So all of these techniques, all of these techniques are very powerful, and they can lead to your performance improvement a lot, and to make your model smaller in size and faster in execution. And with NVIDIA, we actually aim at supporting you through the whole AI productization cycle. So from data collection to training of your networks, to network optimization, and finally to network deployment. And many people know us as a GPU company or a gaming company, but we are actually a platform company. So we've been developing CUDA for many years already, and we actually have more software engineers than hardware engineers in our company, meaning that our focus on software is large. And we also develop many software products which are free for commercial use and which can assist you in developing and deploying your networks, also on embedded and edge devices. So let me introduce a couple of our software products which you can use for free in order to make your development and deployment more efficient. And the first such product is the Nvidia Replicator, which is an extension of our Omniverse platform. Omniverse platform is a platform for creation of metaverse and virtual worlds, and you can also program some extensions on top of it. And Nvidia Replicator is used to create synthetic data. So underneath, it runs a set of domain randomization techniques, using which you can then create a huge variety of different data sets. It also has an extension for robotics specifically, which is called Omniverse Isaac Sim. And the QR code I'm sharing with you is basically a free DLI training. DLI is our Deep Learning Institute, which you can use, and you can learn how to use this software. Another contribution of NVIDIA in the space are our NVIDIA pre-trained models. So we collect and curate huge data sets for many specific tasks, and then we train our models on these data sets, which you can use them for production, also for commercial use. And we basically have two categories of models. The first one are the so-called pre-trained task-based models, which include model for people detection, license plate recognition, gesture classification, and many, many other models. These models you can download from our NVIDIA NGC catalog, and you can integrate them in your application and use just out of the box. In addition to that, we also have some generic applications for image classification, image detection, for segmentation. We also have some transformer architectures there, like vision transformer, deformable deter for detection. So it's a powerful set of models, and you can use them using transfer learning in order to learn some new capabilities. And in order to use transfer learning, we also offer our software called Nvidia Tower Toolkit. Nvidia Tower Toolkit is a zero-coding framework to train artificial neural networks. It includes, scripts for training, but it also includes such optimizations like network pruning and quantization-aware training. And it can, of course, run on any NVIDIA cloud devices and workstations. And it also includes data augmentation in order to further extend your data set. One also important feature of Tower Toolkit is that it supports multi-GPU and multi-node training. You know that modern trainings, they can be really heavy in compute and sometimes require more than a single GPU. And those of you who have trained distributed models, you know that it's usually a hassle to distribute your training across multiple GPUs. So in Tower Toolkit, it's very simple. It's just passing a single parameter. It also offers the so-called automatic mix precision, which can further optimize your training time, and it can also allow you to use batches big in size. And as I already mentioned, it includes pruning and quantization. And in the nutshell, the process of development with our technologies looks like follows. So you go to the NGC, you download the pre-trained models. You can use synthetic data created in our Omniverse, and you train it then in the NVIDIA Tower Toolkit. And then we have a set of deployment tools, or our deployment SDKs, which you can use for inference. And one such powerful tool which helps you in your inference is our Nvidia Tensority. And this is really my favorite piece of software, because it includes all the optimization techniques which I have mentioned before. So it has latent tensor fusion, quantization, post-training quantization, dynamic tensor memory, and multi-stream execution. It's an optimizer, optimizing compiler, and a runtime. So once you have optimized it with Tensority, and it's basically as simple as pressing a button saying like, hey, optimize me this network. And once you have optimized it, you can use Tensority runtime to integrate your optimized architecture into your C++ or Python application. So it's very powerful. Another great piece of software, which is, by the way, open source, and we host it on GitHub, it's called Nvidia Triton Inference Server. And this is our versatile and flexible serving solution for AI models. You can create your models in no matter which framework. Is it a PyTorch? Is it TensorFlow? Is it Tensority optimized model? You can even implement your own custom frameworks, like for tasks like pre-processing and post-processing. So you can run this all in the backend in the optimized way. The cool feature of it is dynamic tensor memory, dynamic batching, meaning that once you get multiple client requests from different sources, you can actually batch them together for faster execution to increase the throughput of your application. And another cool thing is also concurrent model execution. So relying on CUDA Streams, you can host several models at the same time on the same physical device. It also supports ensembles, so if you have the pre-processing and post-processing and then a couple of models chained together, it all can work seamlessly in the so-called zero-memory copy fashion. So it even can run on CPUs. So when we say it's very flexible, we really mean that. The next technology, which is specifically developed for video analytic applications, is our Nvidia DeepStream SDK. DeepStream SDK is a software based on GStreamer framework. Those of you who work with video, you may have tried GStreamer before. And we basically just enhanced GStreamer with GPU-accelerated plugins. And the great thing about DeepStream that it relies on the so-called pipeline efficiency with zero memory copies. Once your data is being moved from the CPU to the GPU, it stays there until the end of the pipeline, being passed as pointers within the GPU. That makes your applications very efficient. And here's a small demo which I've developed a couple of years ago, so using all these technologies. I've basically downloaded the model trained to detect people, and I've trained it on some public data set for hand detection. And then I chained this model for a gesture classification model. And I deployed it in the DeepStream using DeepStream SDK. We've hosted it on GitHub, so it works quite well. And important to say that this is a pre-recorded video, but it runs real time on my Jetson AGX device, which is like a small embedded device. 2 models, but works really smooth and in real time. That's another kind of example you can do is DeepStream. So you see like there are IDs, and you can track people there. You can chain multiple models, as I mentioned. So this model detects vehicles and road signs. And if it detects a vehicle, it can say, is it a van or a sedan, being chained with a second classifier. And to sum up, there are many ways in order to improve the performance of your model, which is specifically useful for deploying AI applications at the edge. And you need to take care of the following things. So first of all, in order to increase your accuracy, you can rely on simulation and synthetic data. And for that, we have tools like replicators and Isaac Sim. In order to further boost your accuracy and performance, you can rely on transfer learning, data pruning, model pruning, quantization-aware training. And we integrate these technologies in our Tower Toolkit. And last but not least, you need to optimize your models. And for that, you can rely on the software product like Tensority. And then you deploy it at the edge using our Inference and SDKs, like Triton and DeepStream SDK. So as models are growing, there is a huge demand in optimizing them. So let's all together make our models more efficient.
Thank you very much, Ekaterina. The time is almost over, but I'm going to ask you one question. There are a lot of questions that you can find in the app, and then you can answer. Like, does synthetic data behave the same as real data, or could it also distort the model?
Synthetic data has a big difference from real data. And of course, when developing applications using synthetic data, we need to take care of the so-called domain gap. And domain gap can be of various types. So you can have different object geometry. You can have different object texture. So it's definitely a trial and error process, and you also need to tweak your data sets. It's a huge challenge on its own, but it's solvable.
And one very fast question. Do all of these tools and models require NVIDIA GPU hardware?
Most of them, yes. But for example, Triton Inference Server, as I mentioned, it can run on CPUs or also on GPUs of other vendors.
Well, the rest of the question, as I said, you can find it in the app. Thank you very much, Ekaterina.
Thank you.
We are going to have now